Well, up to this point, we've been working exclusively with one-dimensional motion situations, whether that is side to side or up and down. But as we know, we don't live in a one-dimensional world, so we need to get to the point where we can start analyzing motion in 2 dimensions. And a very extremely useful tool to be able to do that is a tool known as vectors. Now, we already briefly talked about vectors, but we didn't go into a whole lot of detail. Just as a reminder, we've got 2 types of measured quantities. Anything we measure in a lab or anywhere else can be really put into 2 different categories. One are what are known as scalars. They are quantities with magnitude or amount, but no direction. So examples would be, for instance, time, distance, speed, mass, temperature. There are others. The other type of quantity, which we're more interested in today, are vectors, which have both magnitude and direction. And up to this point, we've really talked about 3: displacement, velocity, and acceleration. There are others, but that's what we focused on so far. So how do we represent vectors? How do I show a vector in a problem I'm working with? Well, if we have here, for instance, some vector A, and it's pretty straightforward. We draw it as an arrow, and there are 2 big pieces here. First off, the magnitude is the length of the arrow. So if you have a longer arrow, that vector would have a bigger magnitude. If you have a shorter arrow, it's going to have a smaller magnitude. And additionally, we have the direction. And direction, unsurprisingly, is in the direction that the arrow is pointing. Now, a real important thing to know about vectors here is that I can actually grab vectors and move them around. That is not a big deal. I can pick them up and move them around and put them in new locations as long as I keep the magnitude and the direction the same. So as long as I don't change how long it is or change what direction it's going in, all of those are totally acceptable. I can move it around all I want. It's not a big deal. Now let's go ahead and add a couple additional vectors here. So for instance, this is vector B, this is vector C. Now how can we combine a vector and a scalar? Well, we usually do that just by multiplying the 2 together. So once again, as an example, let's say I start with A. Well, I could, for instance, have 2A, so I just multiplied A by 2, the scalar being 2, and as you notice, it's still pointing in the same direction, but it is now twice as long. Additionally, I could have 0.5A or 1/2 A, same direction, but only half as long. So the length is proportional to the magnitude, and that's really important. So if I have multiple vectors, I have to make sure their magnitudes are represented proportionally by the length of the arrows. And additionally, if I multiply by a scalar, I either grow it or shrink it based on whatever it's multiplied by. If it's more than 1, it's going to grow. If it's less than 1 and between 0, it's going to shrink. Additionally, what happens if I multiply it by a negative scalar? Like what happens if I multiply A just by -1? Well, I'm just going to flip the direction. So it's the same length, but now it is going in the opposite direction. I've put what is called the tip of the vector on the other end and the tail of the vector on the other end. Well, if that's how we combine a scalar and a vector, how do we combine multiple vectors? And the first way we're going to do that is just by adding them. There's multiple ways we can do this, but to add vectors, we are going to, for instance, have some vector A and some vector B. These are the same vectors we looked at earlier. They're the same length, same directions. They've been moved around, but remember that doesn't matter. And we're going to see that we employ something called the tip-to-tail method. It's pretty straightforward. All we have to do is we have to make sure that the tip of one vector is connected to the tail of the second vector. So this is tip to tail because I've got the tip of one vector connected to the tail of another. So I have this here, but now I go from where I started to where I ended, and I go in a straight line, and this was A plus B. So A plus B goes from the start of the first vector and goes to the end of the last vector. So this is often called a resultant vector. The resultant vector just means the result of a combination of multiple vectors. So A plus B is that new vector, but the biggest point I want to get here is this, because this is where I find that most people make mistakes, is that it starts at the same place the vector starts. So although this is tip to tail, that the tip of A is touching the tail of B, A plus B is not being added here. We are creating this new resultant vector A plus B. So we do not connect the tip of A plus B to the tail. No. Okay. We've already done the tip to tail method. Now we are just drawing our new vector, and we start where the vectors start and we end where the vectors end. Now, one thing we do want to note here is that, for instance, I can actually switch the order I did A and B, and we will see, well, apparently that's where that is, but we can see that I still start here, I still end. A plus B is still the same vector. So it doesn't matter what order I add vectors in. Just like regular addition, doesn't matter what order you put the numbers in. It does not matter, a basic commutative property, and basically we're still going to get the same resultant vector. Well, we added vectors, but can we subtract vectors? Yes. And it may sound a little complicated, but it's actually very simple. We just need to remember that subtracting is really the same thing as adding a negative. And we keep that in mind, it's pretty simple. So for instance, let's say okay, once again, we're still going to use the tip to tail method. I have A and B, and I want to create B minus A. All right, so I'm going to start with B, but I want minus A. I don't want A, so I'm going to actually flip A and create minus A, but now I'm going to still do tip to tail. I'm going to put the tip of B at the tail of minus A, and my new vector, B minus A, oh, let's make sure my color is right here. Let's stick with yellow since we already did that. My new vector is going to go from the tip of B, sorry, the tail of B to the tip of minus A. So I still start in the same location, end in the same location. That's crucial. And this would be, for instance, B minus A. That would be that vector there. Now, one thing we would need to be careful of here is if, for instance, we instead had done, let's say, see, now I've made things a little complicated here, but we'll just use this one for a second. If I had done A minus B, so if I have A here, I have B here. Now keep in mind, if it was minus B, this really should be flipped. I'm just drawing this for a second just to show you. So this would actually be pointed to the left here. And we would see we would get a vector that actually goes up to the left. It would actually be the opposite of this one. So the point being that you would end up with a vector of the same length, but the direction would be wrong. Which makes sense, because in subtraction, the order of the numbers matter. Same thing here. When we're subtracting vectors, you have to start with the first one, B, and then add the negative A. We can't go the other way around. You have to go in the same order. Now, this is going to seem a little out of left field, but it's going to be really, really useful in a minute. So how do we break down a single vector into what are known as component vectors? Essentially, I'm taking a resultant, and I'm creating the original two vectors that made that resultant. I'm going backwards with vector addition. Now, this is often also known as vector decomposition, or decomposing a vector, which makes sense, decomposing, breaking down. So let's go ahead and see what this looks like here. So let's say I have a vector A. I want to break this vector down into its respective components, and you might be thinking, okay, well, really, there are unlimited possibilities. I could have many, many different combinations of multiple vectors that, if I add them together, start here and end here. But when we are trying to decompose or break down vectors, particularly in physics, we're really trying to do it in a very orderly fashion, and that usually means we're trying to break it down, we'll come back to that in a second, in a horizontal piece and a vertical piece. I want to figure out what is the horizontal component, otherwise known as the x component of this vector, and I want to know what the vertical component or the y component of this vector is. So I want to take a horizontal vector and a vertical vector and combine them to make this new vector A. Now, This is really going to take advantage of trigonometry, specifically sine and cosine. Because if we look here, we've gone ahead and defined that this vector A is some angle theta above the horizontal axis. Now, you would have to be given that or some other numbers in order to do this effectively. So, I'm going to say that I want this vertical or this horizontal piece, which we will label A sub x, and a vertical piece, which we will label A sub y. So this is the horizontal component, and this is the vertical component. Well, how can I do that? Well, I can relate A to AX and A to AY using cosine and sine. So cosine of theta, well, that is adjacent over hypotenuse. So that would be AX over A. Sine of theta is opposite over hypotenuse, or AY over A. So if I want to solve for AX and AY, all I have to do is multiply A by cosine theta and A by sine theta. Just multiply this across in both situations, and by doing that, we get this algebraic equation here. Now, I want to be real careful that if we look, AX is cosine theta, AY is sine theta. That's not always going to necessarily be the case because it depends entirely on where we define theta. Because what happens if I define theta here? Well, then my AY would have been adjacent and my AX would have been opposite. And if that was the case, I would have to flip the sine and cosine here. So we just want to be very careful, which is whenever you are looking at some angle and we want to look at the two pieces respective to it, the horizontal and vertical piece, just make sure, don't necessarily jump to, oh, the x is cosine, the y is sine. Instead think, okay, well, what is adjacent to this angle? That will be times cosine. And whatever is opposite of this angle will be times sine. So let's start to look at an example of two-dimensional motion and how vectors can give us much more specific information. So let's say we start at this position, the origin, and we go 50 meters, we'll say up, that's fine. We go 30 meters to the right, 20 meters down, and 70 meters to the left. And the question is, you remember, if we want to know the total displacement, what we would do, remember, that's going to connect from your initial position to your final position. So we should get something that looks like that. Our resultant, which in this case would be delta x, would be starting at the origin and ending where 70 meters ends. And the question really comes down to, well, how can I determine the magnitude of that displacement? And how can I determine the direction of that displacement? Because the displacement is a vector. So it needs to include both the magnitude piece and the direction piece. Well, how can I go about doing that? Now, most of you probably can do the magnitude pretty easily, because if you look at this, you might be able to think, okay, well, if I played around with this, I could definitely figure this out, keeping in mind that this right here is a right angle. You could probably piece together the magnitude, but the direction is going to be a little harder. So what we're going to do instead is we're actually going to go step by step through a process that for this situation will be pretty basic, but we're going to see in a second with a more advanced example that this process, if you go through this, you can piece it all together. No pun intended. So let's start with our first step, which is we're going to set up a coordinate system. So I'm going to start, though, at my origin. So I want the place where I first started my combination of vectors, that is the origin. Make that the origin and make my life easier. And I'm going to define this direction as positive y, negative y, and this direction as positive x and negative x. I didn't have to do it that way. I could have done it another way, but this is the simplest way to do it in this particular situation. Now, I'm going to break down or decompose my vectors into x and y components, or horizontal and vertical components. Lucky for us, in this particular example, our four vectors, the orange, the yellow, the green, and the blue, well, they were already in horizontal and vertical directions. There was none that were some combination of the two, so we can kind of skip this step for now. Now I'm going to rearrange the components, or in other words, the various vectors here, into a right triangle where the hypotenuse will be my resultant. Okay, so let's kind of show how this is done. You can already figure out this here. In this particular example, it's not going to be too complicated. But if I go orange, the best way to do it is to combine all the vertical pieces and then all the horizontal pieces, or flip it. Do all the horizontal pieces and all the vertical pieces. So let's go ahead and do all the vertical first in this situation, since we started with a vertical. So I've got the orange one going up, and the other vertical one will be the green. So I'm going to move that green tip to tail. So the tip of the orange hits the tail of the green. Okay, we're good. So now all my vertical pieces are combined. And now I'm going to combine all my horizontal pieces. So I will take the yellow and go tip to tail of the green. So the tip of the green hits the tail of the yellow. And lastly, my blue, well, that's already there. The tip of the yellow touches the tail of the blue. So if I look, I see that I have ended up with this right triangle, which granted is the right triangle you had already seen. I know that, but now we've seen it in a little clearer way that we know for a fact by adding all the horizontal and vertical pieces individually that this is definitely all there is. Okay, so how can I figure out the magnitude of this hypotenuse given this right triangle? Well, we can just use the Pythagorean theorem. So for the magnitude, I'll even write the magnitude here, we use the Pythagorean theorem. So if I recognize that, okay, so this was going 50 up and 20 back, so this piece here was 30 meters. And if I went 30 meters to the right and 70 meters to the left, this piece here is 40 meters. So if I want to know delta x, okay, well, most of you can probably recognize that this is a 3, 4, 5 right triangle, but just in case, you can write out my Pythagorean theorem, 30 squared plus 40 squared equals delta x squared. Solve for delta x, we get 50 meters. And secondly, I want to be able to figure out my direction. And this is the part where you might be a little more unsure of what to do, but we're just going to use trigonometry. Now we're going to specifically use the angle that is between your initial starting vector and the resultant. So for instance, I have this angle here. And how can I solve for that? Well, the tangent of that angle, and really I could have done sine, cosine, or tangent in this particular situation. If you get more of a fractional or decimal answer for delta x, it's a good idea to use these two since we know them for sure. But the tangent of theta is 40 meters over 30 meters. I solve for theta by doing the inverse tangent, tangent to the -1 function, and I get 53 degrees. So this theta here would be 53 degrees. Now, but 53 degrees could refer to 53 degrees in any direction, so we need to be very specific on what we mean by that. And there are two ways we can do it. One, I can say, well, typically speaking, like in your math class, we say starting at the origin and going this way, we define as 0 degrees. And so I can start there and go around till I reach my vector, my resultant vector, and I can see that would be 90 plus 53, so that would be 50 meters at 143 degrees. If you just leave it at that, I'll know what that means. But another way you can do it that might be a little more helpful if you're trying to be more physically descriptive is I could say 50 meters at 53 degrees, and this is specifically going this way, left of the positive y-axis. So I look at my nearest axis, I define it in relation to it. If instead I had been looking at this theta, I could have said it is some amount above the negative x-axis, but we didn't have that here, so this would be the more acceptable answer. Well, that one was pretty simple. Really, you constantly could have even figured it out without much knowledge of vectors. So let's do one where knowledge of vectors is way more crucial. Let's actually go back to an example we were already looking at. Let's look at A plus B, and we already said that, okay, that is this resultant, A plus B, starting at the tail of A and going to the tip of B. Now, so what is the magnitude and direction of A plus B? Now, currently, you could not answer that because there were not enough specific numbers here. Like, what is the magnitude of A, the magnitude of B, what are their directions? So I'm going to go ahead and set some specific values. Let's go ahead and say that A is 3. I'm not going to worry about what the unit is. It's just some generic vector. And B is 5. And we'll say that, okay, now how we say this is that A is 30 degrees we usually say above, I'll even write it out here. So we usually say it would be 30 degrees above the horizontal. That is how we would define the direction of A in this circumstance. And what I want you to notice is, okay, well maybe you could think, okay, well let's make a right triangle here and here, but as you can clearly see, this angle here is not 30 degrees. So if I set up a right triangle right here, that's not enough. That's not going to give me the right angle, and that therefore tells you it's not going to give you the right answer whatsoever. So we need to go in a slightly different direction. Let's go through the steps one at a time. First, we need to set up our coordinate system. So I'm going to go ahead and do that, and once again, we make the origin where we started. Okay, so that's going to be the start of your resultant vector, should be the origin, and I'm going to have my positive and negative y-axis, my positive and negative x-axis, just for simplicity. Now, I'm going to break down, okay, well first off, so we've set our origin, we've set our coordinate system, so now we're going to break down the two vectors into their respective components, specifically into horizontal and vertical components. Now luckily for us, B is already horizontal. We're going to say it is at least. So B is horizontal, so it's done. But A is not. A has both a horizontal and a vertical piece. So I'm going to break that down into AX and AY, keeping in mind that 30 degrees applies to these two. So I can solve for AX and AY, and I could see now, looking again, that remember AX would be A cosine of 30 degrees because it's adjacent, which if I solve for 3 cosine of 30 degrees, you plug that in your calculator, don't try to do it in your head, I get about 2.6. And AY would be A sine of 30 degrees, or 3 sine of 30 degrees, which is 1.5. All right, now that I've made these two components, those two components are the same thing as A. They add together to make A, so I don't need A anymore. So I'm going to get rid of that, because I don't need that at this time. Let me go ahead and write this out so we don't forget that is 5. I don't want A anymore, so I'm just going to chuck it out. Because now I have AX and AY, they combined make A, so I don't need it. I've got two new vectors instead. And now that we've done this, we have basically done that piece. We need to rearrange this vector into a right triangle. So let's first off combine all the horizontal pieces and all the vertical pieces, remembering that we can move vectors around without changing them. So I have AX here, so that's horizontal. I want the other horizontal piece, which will be B. Keep in mind B was equal to 5. There we go. And then from here, I need my vertical, so that's all my horizontal pieces. I want my vertical piece, AY. And if you look, the resultant is exactly the same, because it does not matter how you rearrange these. And therefore, this is way, way, way easier to analyze, because I have now made a little right triangle with a new angle theta. This is not 30 degrees. This is a new, can't write theta here, new angle theta. It is not 30 degrees. So, how do we determine the magnitude? Well, we just use the Pythagorean theorem. And I say that this horizontal piece would be 2.6 plus 5. I square that part. The vertical piece is 1.5 squared. And I'm solving for a plus b squared. And when you solve that out, you get about 7.75. So that would be the magnitude of a plus b. And if I want to know the angle or the direction, well, I can just do tangent of theta is 1.5 opposite over adjacent over 2.6 plus 5. So if I'm solving for theta, that's the same thing as doing tangent to the minus 1 of this. And I get about 11.2 degrees. So this is 11.2 degrees, and this would be about 7.75 right here. So therefore, A plus B has a magnitude of 7.75 at 11.2 degrees. Now, this one was simple for the direction because it was already defined from what we usually say is 0 degrees. But if you want to be real specific, I could still say 11.2 above the positive x-axis. It's very important you mention positive or negative. If it was above the negative x-axis, it would be over here, and that is not what we want. So what is the main takeaway? What are the main takeaways of our discussion of vectors? Well, can we represent vectors as arrows? Keeping in mind the length is proportional to its magnitude, the direction is represented by the direction the arrow is pointing. Can we multiply vectors by scalars and scale them appropriately and or flip them if it's a negative? Can we add and subtract vectors using the tip-to-tail method? This is really crucial. We have to always remember tip-to-tail, and keeping in mind that when we make the resultant, that is not tip-to-tail. You're starting from the tail of the very, very beginning, and you're going to the tip of the end. It should be pointing in the same direction as your vector combination is. Can we break down vectors into components, specifically in this class looking for horizontal or x components and vertical or y components? And can we determine the magnitude and direction of resultant vectors? Going through those steps, making a coordinate system, breaking down any vectors that are a combination of horizontal and vertical into their components, rearranging these components into a right triangle, disregarding the original vectors, using the Pythagorean theorem to find the magnitude, and using trigonometry like tangent, sine, or cosine to find the angle that we define either with respect to 0 degrees or with respect to one of the axes.